How do you do? No worries. Nice to meet you. Thank you very much. Thank you. Okay, thank you.
Thank you very much, Matt. Do you know, and also thank you, Fiona, for inviting me to give this first of your lectures, as it were. Although I'm a little bit concerned that you have had me wired up. All I need is 2 antennae coming out of here. I've got battery packs around the side of me, and microphones sort of coming in all directions, as it were. So please forgive me, as it were. Next time I'll put a couple of little horns on that. But reflections on the causes of engineering failure and poor performance. This is really, I suppose, a resume, a summary of some of those things that perhaps one has learned over a career, perhaps spanning just a few more years than one would care to admit to, as it were there. But if you did your mental arithmetic when Matt was talking, you'll see that it was sort of 40 odd or so years, as it were, that I've been looking at. Failure, poor performance, is usually attributed in some way or other to uncertainty. That can be uncertainty in a great many ways. It can be uncertainty in areas of judgment, or it could be technical uncertainty, because in engineering we do not live in a very precise world. Science takes us so far, and then we have to take judgment a little bit after that. If we look at areas of judgment, what I've generally found is that they divide into 3 groups. What I would call the genuine mistakes. Somebody perhaps knows what should be done, but for some reason makes a mistake there. Or it might be from inadequate or poor training that has occurred, and the person has been put in a role or set in a crisis situation where training has just broken down for some reason. Then there's the area of inactivity, where there's been really no malicious intent, I think, to cause a failure there, but people have just not taken the appropriate action when they've been presented with a situation. They've complied with a situation rather than go to attack that situation in order to get something that they were feeling a little more comfortable with. There is, of course, the deliberate acts. Malice you don't see so very often when people are discontent about something or they're unhappy with a situation. They deliberately go and cause a failure. You do see, surprisingly greatly, a number of non-observance of rules. There are rules, there are safeguards, and for good reason. Good reason as they think, in trying to get to a maintenance situation or things of that sort of order, they remove those safeguards. Floor plates in engine rooms, sometimes see them totally missing, as it were. And shaft guards and various rotating machinery guards. Oh, it's always going wrong down there, let's just get rid of that for the moment. Well, that's fine until the floor plates get oily and the ship starts to roll a bit in that way. And it wouldn't be the first time I suspect many of you there have sort of slid from one side of an engine room to the other on very greasy and oily floor plates in those sort of conditions. Then there's the questions of technical uncertainty. We know a lot about corrosion. We know a lot about fatigue and creep and brittle fracture. But there is still an awful lot that we have to learn in those areas. So there is uncertainty sometimes in our calculations. When we think of control there, that can be either system control, where you've got many interacting layers of control coming in, and you get a bug or something in one layer, and then you find it tends to take its way through, and you get some rather called for or uncertain things that are happening in the total system. Sometimes it's a safety critical systems. And then there's the environment. That can either be natural, operational, or the managerial environment in which these things are working. So uncertainty lies at the root of so many of the failure and poor performance things. Failure is not new. We can trace it back for different reasons. Failure, some of those are poor performance, some of those are total failure. But this one is perhaps marks the one of the more significant areas, apart from giving rise to many films and stories and what have you. It gave rise to the first international convention on the safety of life at sea in 2014, in 1914. So that's interesting actually, just literally 100 years away from that. That was attended, that was such an important failure. It was attended by 16 heads of state there. And it gave rise to the things that we take for granted today. The ice patrol, life-saving equipment provision, or adequate life-saving equipment there, radio telegraphy, the need for a stern power. It might seem surprising that there wasn't a requirement for a stern power in ships at that time. But it was only a few years before that there were sailing ships, as it were, and design tends to involve the need for safety certificates, subdivision, passenger numbers, all of those sorts of things. And so what I thought we might do, with your permission, over the next 15 minutes, 55 minutes or so, is to try and tease out, both from major disasters and also some of those things that we have seen where we've had little failures occur, perhaps a shaft has broken, perhaps something else has happened there. See if we can find any common threads through those failures that we might draw lessons and tease out for our future use. Of the major disasters that I'm going to look at, obviously known to most of you there, the Herald of Free Enterprise, Piper Alpha. Quite amazing at the height of that disaster, the actual amount of natural gas that was being burnt was equal to the UK consumption there on an average time. So it gives you some idea of the intensity of that inferno. Scandinavian Star here. The Nimrod, I thought we might have a look at, of 2007, those areas. Ramsgate, again, just a little earlier. I'm not going to look at Costa Concordia at the moment because there are still issues outstanding for them. It is still too new, I think, to distill those lessons in the wider context. Although I think you'll see that there are a number of parallels from all of these that one can see in that particular case. But I'll first start off with just a few cases. Short, stiff shaft line dynamics, the sort of propulsion shafts that you see in tankers and you see in bulk carriers. Very short shafts, very stiff, very little room for manoeuvre or movement of the ship around it there. Now, in recent years, from ships being built in the Far East, we have had a tremendous number of failures there. Either failures, let me take this other little weapon, either failures in those bearings or failures of that coupling flange there onto the main engine. There. In that case, it has been largely because one hasn't got the slope right between the bearing and the shaft. In here, the shear force and bending moments have not been right either. Yet, if we go back to the 1960s, mid-1960s, when I first started to come into this industry, we had exactly the same problems, except that was a steam turbine. That was a steam turbine there, and there was a gearbox sitting there. the problems that we had in aligning those shafts to the aft end of the gearbox main wheel flange, there was shear force and bending moment. We learned some very valuable lessons, and if you go into the Institute of Marine Engineers, Institute of Mechanical Engineers, many of the journals, this was public. You could fill this room with the publications that went on at that time. Similarly, at the other end, we found empirical ways of getting the correct alignment between shaft and bearing. Again, equal amount of information. Yet somehow, that never found its way to the Far East, and we've been condemned to committing exactly the same mistakes as was happening at that time. And what you tend to find is, in this whole area of transfer of technology, that it is essential, if we're going to avoid failure, to transfer it not only within companies. Often people think of information as power, and they keep it sort of tucked away down here somewhere. But one has to let that information flow, because otherwise people will make the same mistake. There was a case, I think it was BAC or something of that sort, or some years ago, had a problem with one of the wings of their aeroplanes, and they crashed it there on a test flight. Managing director of that company called all his competitors in, so they shouldn't make that same mistake again, because it was safety critical. And then there's this other little thing here, corporate amnesia. It's a pure Carlton term. But the number of times I've gone into companies when they've had failures there and said, this failure with the Jolly Roger, let's call it, whatever, didn't you have something like this about 7, 8 years ago? No, they say, we don't, never seen this sort of failure before. And you say, but yeah, wasn't it something to do with a coupling or a torsional? Oh, I do remember somebody talking about that. Why don't you get the fire? Oh, we threw those all out after 4 years because we don't believe in keeping fire. Okay, so you have to put this problem right again, and you start the learning profile again, and you pay $250,000 in the process, as it were. You know? So there's a great thing that we do need to remember, that transfer of technology is important, both within companies and also externally, when areas of an industry move from one part of the world to the other. Then we come to the rate of design progress. In the early years of this century, we saw a significant number of these failures on the raceways of polypropulsor bearings. What was happening at that time was that if we look at the years and we look at the power output per shaft, that some of these designs were not actually going on sea trials, and they certainly, the feedback from sea trial, from service, was not coming in before units of considerably greater power were being put out. Look at the way that curve's going. Now you might have thought we would have learned that lesson, because if we think back to the 1970s, when tankers were going from 150,000 tonnes to 250,000 tonnes to 500,000 tonnes there in very, very short order, we had any number of fatigue problems. And this always seems to happen when you let the rate of design progress get out of the or out of kilter with the amount of information that is coming back from service. Again, engineering is not a precise science. Then there's the learning of the lessons from the past. This, as you can see, was a ferry boat. And it had a rather revolutionary type of stern that we saw here. And it produced a very severe wake field. Very, very, very tight, velocity gradients in there. The industry learnt then that the severity of the wake field is important with that ship when you cross the North Sea in it. If you went at one start of the journey and you just put a pen mark on the bulkhead there, the transverse bulkhead in that ship, where you thought the crack was, and then after 6 hours of belting across the North Sea at full power, you would find that crack had grown by about 5 millimetres, as it were, when you measured it at the other port, at the other end. So therefore, the welding gang came on and things of this sort. Well-known thing in the industry. Yet, 5-6 years ago, second-order harmonic pressures of 22 kilopascals. For those of you not familiar with that, what they should be, you start to get worried if they're greater than 3, as it were there. And this was purely and simply because people had not bothered to do their model testing correctly and understand what was going on in there. What one actually found in this case was that the water was going backwards through the propeller disc at the top because of the way the ship had been designed and the problems that were occurring at that time. We must learn the lessons of the past, because otherwise we just accumulate failure after failure. Georges Santayana, he was a historian, and he was thinking of wars between nations, discord between countries, whatever. And he said, those who do not remember the past are condemned to repeat it. He might just as well have been thinking about our own engineering industries there. Because if we don't remember what went on before, we throw records away, so on and so on. Then we are just throwing away our information. And as sure as eggs are eggs, if you want an expression like that, we shall fall into those same traps. I've found throughout my life that failure occurs in cycles. Depending on the sort of failure, it might be 5 years, 7, 10 years, or perhaps even 15 years. But you see this cycle that comes along. Another interesting area there, insufficient attention to detail. This is the main pinion, it's a beast of a thing, of an ice-breaking oboe vessel, the oil and bulk carrier. Been in for maintenance, and somebody hadn't cleaned out the gearbox properly after the maintenance. Little tiny piece of metal, you can just see it there. No bigger than that. There. Got caught up in the mesh, churned up in the oil. There. Got cold welded to the surface. Caused a fatigue failure sitting there. And there was the damage to the tooth at the end of this, process. Another example here. For those of you who know piston rods, that should be perfectly straight. I mean, it's a beautiful testament to the ductility of that metal. But you can imagine when it, instead of being straight and connected to the piston, to the conduit there, you can imagine what it did to the inside of the engine there. Caused because somebody had not read the tightening sequence and instruction on these bolts here. The whole lot fell apart. So, inattention to detail is again a major issue that is coming on. Not fully understanding the consequences of an engineering decision. In this case, designer of a high-speed craft wanted to lighten the weight of the craft so he could trim it more easily. So instead of using a model shaft, which was the tradition, he decided to go titanium, and it worked very well. Yes, it did reduce the weight beautifully, but he forgot there, or didn't even think about the issues with changing from model to titanium. he machined the titanium shaft with the same tool angle settings that he had used for model. And that was abusive machining. He created a whole series of little tiny notches in the shaft, and those notches you could almost write on there, please crack here, as it were, because it gives a start for fatigue failure. Here, the designer had decided to go for a 1 in 12 taper. There's nothing wrong with a 1 in 12 taper. But if you've got such a steep angle, you've got to have very great control and space to have control over pushing up whatever the mating member is at that point. Where this was actually being set up was a very tight corner of the engine room. And so there wasn't room to get the necessary control over, and didn't achieve the contact fit. And as you can see, fretting fatigue was the result. There, the thing lasted 2 days. Fortunately, that one didn't kill anyone. That killed 12 people, as it were. The achievement of the design intent there, where this is all about the ability of designers, production engineers to understand each other's problems. There. It's essential with this sort of situation for experienced engineers to stand back and start to think about the design concept, both in its concept, the detail, the production processes, how that integrate with other systems. Because again, my experience tells me that failures occur at the boundaries of systems there. Operational expectation, good example of it here. This is the inside of a diesel engine gudgeon pin, big thing, so with a hole down the middle, and you're looking at the hole. The designer put a very nice little radius curve here for this oil way. But somehow somebody had to get into this central hole with a tool of some form and perform this drilling operation and this machining operation in this plane. They did the best they could, but put a load of quench cracks, and hence you can see a fatigue failure starting there. So it's not a coming together of all aspects of the design and production process. Education and experience. I was very dismayed in a former life to realise that many engineers who were well qualified engineers, ostensibly, couldn't tell a piece of brass from a piece of steel, as it were. I instituted training sessions for people who you would have expected having got first degrees or second degrees in engineering there, such that at least they could recognise something that looked a bit like that, say came out of the copper stable there, and steel, and you could not make a total and complete idiot of yourself because you'd learnt your materials through Young's modulus, Poisson's ratio, density, and things of that sort of order. Similarly, continual professional development is essential, providing it's conducted honestly. Now, I've lost count of the number of times when I have gone into give a lecture into a conference, and this conference has been 2 days, 3 days, whatever it was. I've only been able to go in there for 2 or 3 hours, give a lecture, and as I'm walking out the door at the end of it, the young ladies on the desk are saying, "Oh, Mr. Carlton, sir, your professional certificate of continuing professional development." Well, what professional development have I actually got for attending a 3-day conference for 2 hours or whatever? These things have got to be done. Honestly, the last time I did that, the last time that occurred was only about 2 months ago. And so one has to treat these things very, very rigorously. This thing This is often a cause of failure. The design intention, the system integration, operation expectation. As I said to you just now, failures often occur at the boundaries of systems. But sometimes designers don't get the correct information, or the correct information flows don't come through the whole of the process. Operation expectation can sometimes exceed design intent. Good example is obviously a cruise ship. She was on her maiden run across the Atlantic. And the critical thing as far as the commercial part of the organisation was that she'd be in New York ready to receive a load of travel agents at 3 o'clock one afternoon. The master signalled the marketing department of this company and said, you know, I would love to be there at 3 o'clock in the afternoon, but unfortunately there's a storm between me and you, as it were. So I'm sorry, I'm going to be late. The next signal comes in from the chief executive officer of that company. Be there at 3 o'clock. So you do that. You can see that deck. It's not, I hosed it down, and you can see they buckled the ship, as it were, in pushing through a storm, exceeding design intent. Management overruling a sea staff sitting in. I'm not saying all management are bad and all sea staff are good, but certainly not the case. But there is another case that is coming up. Change of ownership. Sometimes when a ship changes from one owner to another, the new owner wants to do something totally different, which is out with the design assumptions of the previous area. This one. Here, operational expectation. That's cruise ship looking down at the propellers. And the owner wanted the fastest cruise ship. And so he said to the builder, go and design me a cruise ship which will go at 27 knots. And for every 0.1 of a knot that you get above that, I will give you money back on the price of the thing. So what does the builder do? He designs a racing boat, basically. Now we all know cruise ships don't work at their top speed, or very rarely work at their top speed. They toddle around depending on where they're going, 5 knots, 10 knots, 12, maybe 15 knots of different things. This ship performed beautifully. The designer got 0.3 of a knot above. And for those of you who know, it's just basically a cubicle. That's a hell of a lot of good design has gone into that in power. But if you were trying to eat your supper in the restaurant at 10 knots, well, Jane, my wife, often says to me when I'm looking a bit tired, she says, don't leave a soup on the menu, will you, because your head might fall into it. It wasn't a case of my head going into the soup. It was the soup at that sort of speed and the vibration coming up and hitting him in the face, you know. And so this is the sorts of issues that come along there. Human factors. I've really only been talking there about 10%, 15% of failure situations. But human factors account for the rest. They might be fatigue, the not understanding of instructions and information that's presented to them, not appreciation of the train of events that follow a decision. Surprising how many people make a decision and not think 1 step, 2 step, 3 steps ahead there. The use of a common language, the number of situations that occur where the crew can't speak to the officers, and vice versa. Information levels. If you give too much in a time of crisis, you may not be able to absorb it, and therefore make a wrong decision. If you give too little, the same may be occurring. Also, you've got to match that information to the educational level of the person who is receiving that information. It's no good giving them an answer which they just do not understand. Human capabilities. There. We are not so far away from the animals. We've got 5 senses. Yet most of our modern systems today there tend to require to use just 2 there, which is sight and sound. So therefore, designers need to take account that it's going to take the human a little more time to respond to a situation where he can't use all of his senses. We're not so far down that evolution chain there that we can adapt so quickly. So we need to understand very much reaction times. Task overload. Often companies will try to reduce staff to a minimum to cut costs. Fine. And that may work in the times when everything is running normally and running along beautifully. However, when you get into a crisis situation, something goes bang, or potentially is going bang around you, this can lead to stress, which can be either mental or physical. And that often results in very serious errors being made. This is a sort of a Carlton thought, I suppose. The management of work so as to avoid human fatigue is essential if errors and failures are to be minimised. A lot of failures occur because that is not dealt with. Human error takes many forms. The operator can do the job automatically, so he's doing his job automatically. Then something happens over there, whatever it is, catches attention. A mistake occurs because his attention has been distracted. They may find shortcuts, disregard some of the rules. Again, ending in disaster. Errors made in situations where the operator doesn't have the knowledge. This is a training one there, which one tends to see fairly regularly. Human behaviour. Important ways. Training is very important in conditioning human behaviour. But when there are situations that you've been working in where things have not gone wrong for a long time, then people will be lulled into a false sense of security there. And if that develops, safeguards get into a state of disreparation, the reasons for them can even be forgotten. A new employee, you might say, right, I'm going to train this chap, fine. But then if he goes out into the field and people say, oh, you don't take care of that, These people supposedly are the old hands at the game. It takes a very brave individual there to stand up to that and say, no, I'm going to do it this way, resulting from peer group pressure there. Fatal flaw in that is to assume the supervisor always knows best. Now they were just sort of situations. I just wanted to look at those 3 cases again, of 5 cases I think it was, so about 1 slide each. If we look at the Herald of Free Enterprise, Mr. Justice Sheen conducted that inquiry there, and he concluded that this court needs say no more than the need for clear and concise orders, strict discipline, attention at all times to other matters affecting the safety of the ship and those on board. There must be no cutting of corners, maintenance of proper channels of communication between the ship and the shore for the receipt and dissemination of information, and a clear and firm management and command structure. I always think the sad thing about the Herald of Free Enterprise was that you go back to the early 50s And here was the Princess Victoria there, on the Larne-Stromeur crossing. In those days, they didn't fit full doors. They only had 1.5, 1.6 metre doors on the stern end. She was in a hell of a sea, got damaged, and the free surface of it was so well known. Yet nobody realised it, who were operating that ship at that time. Her designers, yes, but in the operation. Piper Alpha, Lord Cullen. I won't read all of those things out, but that was before, that was after. 2 work permits had been issued, but they're not being cross-referenced there. Work on one wasn't complete when another shift came along and started work somewhere else. That work was completed satisfactorily. Then there was a need to start the pump was completed. I'm paraphrasing that lot there. That pump started there, and the loose cover that had been temporarily used as a blanking plate on the job that wasn't completed, that wasn't known about, led to a release of hydrocarbon, and hence an explosion. The sad thing there is that management had known there was a failure in this whole process of recording jobs and recording the whole processes there. Inspectors had been on the ship, on the platform before there, and had also come up with same issues, but they hadn't actually learned and implemented those lessons. Scandinavian Star. That's her when she was towed into Eskilde. The fire brigade were trying to finish the job off. There. 2 separate fires were started by an arsonist. The first one was discovered and put out. The second one wasn't discovered for some time. The fire took hold. The cabin partitions were made of a material which released hydrogen cyanide and carbon monoxide, deadly cocktail, as it were there. There were various maintenance issues with watertight doors that had to be closed manually there, and with alarms. The Filipino crew members couldn't speak English, and the Norwegian officers couldn't speak Filipino, they could speak English. They'd never conducted a fire drill on that ship there, so they hadn't got a clue what to do when problems occurred. There was a total lack of knowledge by the officers of the air conditioning system and the exhaust plants for the car deck. And communications on the ship had failed because the captain believed that all the passengers had been rescued, and then he and the crew took to the boats there, and there were passengers still on board. Then there was Nimrod. Mr. Haddon Cave found. Well, actually, before one looks at that, I think his title for his report was really quite interesting. A failure of leadership, culture, and priorities. He found that the loss of the Nimrod was due to a general malaise there, caused by a drastic reorganisation and cost-cutting. And this dominated the mindsets of everybody involved. The separate organisation for safety there, which would have actually recognised some of the issues, would have had been disbanded and abolished. Project teams were set up which had to look after safety, and as well as the management of spares, maintenance and what have you. So the need for safety had to compete with the drive to cut costs. Rather sad story. All the crew were lost of that particular one after the aeroplane had been refueled. The Ramsgate link span there. Chapman's report to issue of civil engineers showed that the prime cause was apparent from the calculations made by the designers and the checkers. They had both made the same conceptual mistake. They had forgotten, essentially, that ships sometimes come in a bit hard on wingspans. And so therefore, and they come in on the skew, and there's tidal drift. And they had assumed symmetry, and not assumed that very well. The checkers, to some extent, had followed the designers. He also concluded that the concept was inept there, because there was not a single assembly drawing, full assembly drawing there, such that the whole process could have been put together. So, when failures occur there, it's important to distill the reasons for those failures in the sense of a no-blame culture. Because as soon as you start chucking blame around, people shut up. There. One needs to sit and rationally analyse that problem there. And then to pass those lessons on to those who may make that same mistake in the future. This is also true of near-miss situations, because those near-miss situations are going to be the situations that come and hit you next, as it were, there, if you don't analyse those situations as fully as you would an actual failure. It's also a mistake, in my view, to involve the lawyers too soon. Because while engineers generally will talk to each other, as soon as you bring a lawyer into the scene, their engineers just do that. They shut up. And I've known failure situations that have had delays there of 5-6 years before the real reasons have been sorted out, just because you don't get this communion of ideas. So, let us wrap these thoughts up a little bit now and look towards conclusions. We've had a very brief, and I recognise it's a very brief look at some of these inquiries. We've also looked at a load of failure investigations. They lead us to thinking about developing the correct organisational leadership and the culture in companies, where there is a free and open discussion. Correct management objectives and responsibility. The provision of the correct levels of training and education, sometimes all too lacking. Developing, very importantly, the correct information flows and adequate communications there. And in the adequate communications, I would include a common language. You know, I've lost count of the number of ships I've been on where the officers can't talk to the crews, in the general sense. There's perhaps 1 or 2 crew members who can understand a form of pidgin English. It's just a disaster waiting to happen. Proper design reviews, controlling the rate of design progress. You know, there's the old saying, you know, we must learn to walk before we can start running, sitting in. And that is often as much business driven as it is a fault of engineering that is sitting. The proper distillation of the lessons learned and the transfer of technology. And I come back again to the reporting of near misses. So, concluding remarks, or if you like, Carlton's view of the world there. I believe that if you're trying to minimise, and you'll never cure failure, because we are just not that clever when we are starting with a blank sheet of paper, as it were there. But to minimise failure, I think you need to develop in organisations an effective leadership and organisational culture. The responsibility of management, I think, is to create an environment where there can be free discussion of safety and reliability issues. Think of some of the examples. Herald of Free Enterprise is a good example. Piper Alpha is a good example. The ship that was driven across the Atlantic, sort of like a Formula One racing car, is a good example of that sort of area. When the failures occur, establish as quickly as possible the root cause of the incidents within that thing called a no-blame culture. It's very difficult to get that sometimes, particularly when you've got competitors coming at you from all angles. But then communicate that as widely as possible. Divorce the safety function from the operational cost management functions there. If you confuse those two, then safety is usually the one that drops out in there. Learning the lessons from past experiences, terribly important, because if you don't learn those lessons, you will actually be condemned to repeat those. Systematic design reviews are absolutely essential, as is operational practices. The importance of risk assessments, again, a very important aspect there. Giving proper training to personnel, but training which not only covers the normal operational circumstance, but the crisis situation, such that when the lights go up in an engine room or wherever, you can almost go to whichever valves it is that you need, blindfold, and take the appropriate action into there. Also, and this again is another training issue, training people to think beyond the immediate decision that they're taking. Again, we have seen this in so many of those examples this evening. If they don't think beyond the first action as to what the consequences of that are going to be, then there is potential trouble. Then there's the importance of presenting information to watchkeepers, operators, whatever, which is consistent with their training, such that they don't have to sift through a load of data and think, what the heck does that mean? And it suddenly dawns on them what that means when there's a bang in the engine room in there. The need for common language, we've said that several times. And operators don't need to be deluged with information. They need the amount of information necessary to make the right decision. That's in part not just chucking everything at them, but perhaps taking some cognizance of really what that is trying to mean. So one is perhaps thinking, perhaps aiding it with neural nets, fuzzy logic and things of that sort of order. And the effective, sufficient and disciplined maintenance. We saw those two very expensive examples sitting there because maintenance hadn't been properly carried out. But we also saw it in Piper Alpha. We saw it in the Nimrod case. So I think I would like to leave the last word with Her Majesty. And it's so true of what we've been talking about today. With the benefit of historical hindsight, we can all see things which we wish we had been done differently or not at all. Okay, she was talking of the Irish situation, but equally it is the same for engineering. Thank you very much for listening.